Hello learners, welcome to another module of Unit 4 of the course on real analysis. In this module, we shall deal with results via which we are able to interchange the limit process and integration and again limit process and differentiation. That is, in this module, we will see results where we can interchange limit and integration and limit and differentiation. The first result that we will see will be something like limit of the integration of the sequence of function fn will be equal to integration of limit of the sequence of function fn, that is integrable of integration of f. So, similarly for differentiation we shall see that limit of the differential of sequence of function fn equals differentiation of the limit of the function, that is d dx of f. We therefore have the following results. So, the first theorem that we have is theorem on uniform convergence and integrability. So, let us state the theorem first. Till now we have seen the concept of uniform convergence for sequence as well as series. So, for this theorem we have first one is for sequences, So, if a sequence of functions fn converges uniformly to a function f in an interval ab, and if every function fn x is integrable on the interval, then the limit function f is also integrable on the interval ab, and we can write limit of the integration of sequence of functions fn x dx equals integration of the limit of the function fn x dx, which equals integration f of x dx. Since here we are considering integrability over an interval, so integration a to b f of x dx and so on. Similar to sequence, here we have another result for series as well, So, if a series of functions summation fn converges uniformly to a function f on an interval a b, and if every function fn is integrable on the interval a b, then the function f is also integrable on a b, and we have summation of the integration a to b fn x dx equals integration a to b summation fn x dx, and since this series of function converges uniformly to fx, so we have a to b f of x dx. So, here we are only interested on the statement of the theorems. So, let us see certain examples first. So, first consider the sequence of functions given by, consider the sequence of functions fn, where fn is given by fn x equals n x e to the power minus n x square on the interval 0, 1. So, now integration 0 to 1 fn x dx, this equals 0 to 1 n x e power minus n x square dx, which equals n by 2 0 to 1 twice x e power minus n x square dx. Now, if we use the substitution x square equal to z and continue with the integration process, so we have this equal to half 1 minus e power minus n. So, this is by the substituting x square equal to z and then following the integration process. Then limit of the integration fn x dx, this equals limit of half 1 minus e power minus n. So, using the limit theorem for sequences, we have half 1 minus 0 equals half. Also, integration of now if we find the pointwise limit, so we have here f of x equals limit n x e power minus n square. So, this equals limit n power x by e power minus n square. So, this equals 0. So, we have therefore integration f x dx equals integration 0 to 1 0 t x, which will be 0. But here we can see that in this case limit of the integration fn x dx is not equal to integral of the limit, right, is not equal to integral of the limit fn x dx 0 to 1, right. Although limit fn x equals 0 for all x in 0 1. So, here then we can conclude that the given sequence of function is not uniformly convergent, because if it was uniformly convergent, then limit of the integration of sequence of function is equal to integration of the limit, but in this case that does not happen. So, therefore, the given sequence is not uniformly convergent. In the interval 0, 1. Now, let us move to the theorem on uniform convergence and differentiability. So, the result that we have, theorem on uniform convergence and differentiability. So, again, since we have the concept of uniform convergence for sequence and series, like in the previous theorem, here we have two results. So, first one is for sequences. So, if a sequence of function f n be such that in the interval a b, first of all limit is f x, that is limit f n x equals f x for all x. Second, the sequence of functions are differentiable for each n, that is f n dash x exists for all n, right. Third, f n dash x is continuous, for all n. And fourth that we have is f n dash converges uniformly. Then f dash exists in a b, in the closed interval a b, and limit of the differentiation of the sequences f n x dash x equals differentiation of the limit, that is f dash x in the interval a b. Similarly, we have the result for uniform convergence of series as well. So, now we have for series. So, if a series of functions summation f n be such that in the interval, a b certain conditions holds true, that is first is summation f n x equal to f of x, that is limit exists for all x. Second, we must have that f n dash x exists for all n. Third, fn dash x is continuous for all n, and fourth, summation fn dash converges uniformly, then f dash exists in the interval a b, and we can say that summation of fn dash x equals f dash x in AB. We now consider an example to illustrate the theorem. So, here we have an example where we consider the sequence of functions, fn, where fn is given by the formula fn x equals nx upon 1 plus n square x square. So, first we will find the pointwise limit of this function. So, here fx equals limit fn x, which equals limit nx upon 1 plus n square x square, right. So, this equals limit x by n if we multiply both the numerator and denominator by 1 upon n square. So, we will have 1 upon n square plus x square. Now, this equal to 0 for all x. Thus, the limit function is, so we have f x equal to 0 and limit f n x equals f x for all x. Now, first we will find the differentiation of the sequence of functions. So, now fn dash x equals, so if we have, so this equals d dx of nx by 1 plus n square x square. So, this equals n 1 plus n square x square minus nx multiplied with n square into twice x if we use the rules of differentiation. So, we have 1 plus n square x square whole square. Now, this equals, cancelling the common terms, we have n 1 minus n square x square by 1 plus n square x square whole square. Now, for x not equal to 0, limit fn dash x equals limit of n 1 minus n square x square upon 1 plus n square x square whole square, which equals limit n minus n cube x square by 1 plus twice n square x square plus n to the power 4 x to the power 4. Now, if we divide both the numerator and denominator by n to the power 4, we have limit 1 upon n cube minus x square upon n by 1 upon n to the power 4 plus 2 by n square x square plus x to the power 4. Now, using limit theorem for sequences, we have this limit equal to 0. However, for x equal to 0, since f n x was n 1 minus n square x square 1 plus n, since f n dash x was 1 plus n square x square square, therefore, f n dash 0 equals n. So, limit f n dash 0, this equals limit of the function n, and we know that this sequence is not convergent, or we can even write this equals infinity. Thus, whenever we include the point x equal to 0, we see that limit of the differentiation may not be equal to the differentiation of the limit, or in particular we can write that thus in an interval like which includes 0, like say -2 to, we can say that limit of the differentiation of the sequence is not equal to the differentiation of the limit of the sequence f dash x. Now, this happens, this is true because the given function, the function f n dash x, which equals n 1 minus n square x square 1 plus n square x square whole square, this function does not converge uniformly in the interval -2 to 2. So, does not converge uniformly in -2 to 2. So, here we can clearly see that from the statement of the theorem, the third point of the statement of the theorem is not satisfied. So, we can say that the limit of the differentiation is not equal to the differentiation of the limit. Thus, in this module we have seen results which can sometimes be also used as a criteria to check whether a given sequence of function or given series of functions are uniformly convergent or not. We just since we have two results for uniform convergence and integrability and uniform convergence for differentiability, and we have seen two of such examples as well. In the next module, we shall introduce power series. Thank you.